Welcome back as we discuss the operating principles of a typical two-pole DC motor. To begin, let's examine the behavior of these two permanent magnets. If the like poles are brought together, they repel each other, and if the unlike poles are brought together, they attract each other. Using these principles of magnetic attraction and repulsion, we can explain the operation of a basic two-pole DC motor. In this demonstration, two electromagnets and their respective pole pieces produce the main magnetic field and represents the static part of the motor. The coils are wired to create the main magnetic field when connected to a direct current supply. With the aid of a compass, we are able to see the direction of the field at each pole face. The needle indicates that the path of the magnetic lines of force extend from a north pole to a south pole and back to the north pole via the iron frame or yoke, which completes the magnetic circuit. Now, to the main field system, we add an electromagnet which is free to rotate, called the armature. This simple two-pole armature has a set of windings which are energized via brushes which ride on a two-segment commutator. Current flowing in the armature windings produces a magnetic field and a pole is formed at each end of the armature where the magnetic flux is concentrated. When energized with DC power, the main poles and the armature poles attract and repel, producing forces which turn the armature. The commutator and brushes, acting like a mechanically operated reversing switch, maintain the correct polarity of the armature poles to sustain rotation. To ensure that the motor runs efficiently, the switching position, or point of commutation, must be correctly set. This is achieved by adjusting the position of the brush gear for minimum sparking and maximum speed. Let's now discuss changing the direction of rotation. This can be achieved by swapping the supply to the main winding or, as demonstrated, by swapping the supply to the armature. We move on to discuss back EMF or counter EMF. Back EMF is the voltage induced into the armature windings as they turn within the main magnetic field. Since the induced EMF opposes the applied voltage, it is called a counter EMF or back EMF. When driven as a generator, the back EMF produced by the armature turning in a magnetic field produces the DC output voltage. When connected as a motor, this back EMF affects the amount of current flowing in the armature. In this demonstration, we can see how the back EMF affects the current in the armature circuit. At switch on, the current flowing into the armature is a maximum, but as the speed of the armature increases, the armature current falls as the back EMF increases. The armature current is clearly determined by the difference between the applied voltage and the back EMF. This concludes our discussions on the basic operating principles of the DC motor. After the break, we will discuss types of DC motors.